Okay, welcome to part 2 of the calculations for kinetic methylene blue with ascorbic acid. We're going to finish number 3 and 4 together in this video. So I have opened the Kinetics lab calculation section right here. I'm on page 7 and we're starting with number 3, and I also have open my spreadsheet. Okay, so I'll work through what all these numbers mean and where I get them. Okay, so once the K observed and concentrations have been determined for each run, and that's what we have right here. So that's 6 runs, concentration for HCl, methylene blue, ascorbic acid, etc. I'll delete this just to not confuse you. And then this is my K observed values. These are all the negative slope of the 6 plots that I made. Okay, so I have those. It says use the method described in the theory section to determine the X and Y values by comparing K observed values from appropriate runs. So let's first look at the theory section, and then I'll explain how this relates to what we've gone over in class. So theory starts right here, and then if you scroll down, you can see that rate is equal to, and I'll make this a little bit bigger. The rate is equal to K observed, which is the observed rate constant, which you wrote down, times the concentration of methylene blue to the power of Z. That's just a placeholder for right now. So where K observed is equal to the actual rate constant times the concentration of H plus, which would be HCl in this instance, to the X, so we don't know what the order of HCl is, times the concentration of ascorbic acid to the Y. So we're trying to solve for our X and Y here in number 3. Okay, then scrolling down right here, 4, 5, and then 6, tells us that we can compare run 1 and 2 to determine what Y is. So if we're looking for Y, which corresponds to ascorbic acid, we want to know what the order of ascorbic acid is. We could compare run 1 and 2. Why? Because the concentration of hydrochloric acid stays the same between those 2 runs, but the concentration of ascorbic acid does not, it changes. And remember when we're talking in class in 16.3, chapter 16.3 from the Silverberg book, we discussed how if we are trying to determine the rate law for a reaction, we need a series of runs or a series of experiments in which only one of the concentration changes between 2 experiments. And we can compare those to the rates, the observed rate constants, the concentrations, whatever information you have to determine what the order of a particular reactant is. Okay, so this tells us we can directly compare run 2 and run 1. And how this is set up is it says K observed, which is your observed rate constant, for run 2 is going to be equal to your real rate constant times the concentration of, in this case, HCl to the X, times the concentration of your ascorbic acid to the Y. Okay, so we're going to do that down here in the calculations number 3. Take a look over here at my spreadsheet. And what I've decided to do for determining the order of Y, I already have my answers here, and I'll show you how I get these. But what I've done is I've made 3 different comparisons. So I've compared run 1 and run 3. Why did I do that? I've compared run 1 and run 3 because the concentration of HCl does not change, but in run 1 and run 3, the concentration of ascorbic acid does change. So that's one comparison I'm going to make. The other comparison I'm going to make is between 2 and 1, which it stated in the theory section. So I'm going to compare experiment 1 to experiment 2. I clicked them out of order, but experiment 1 to experiment 2. And notice that hydrochloric acid, again, does not change. But in experiment 1 and 2, the concentration of ascorbic acid does change. Okay, so that's going to give us information about how ascorbic acid affects the rate of the experiment and what the order of ascorbic acid is. Okay, so before we actually do that calculation, let me show you how this is laid out. I'm going to scroll over. So next to all the concentrations are over here to the left, I have a column that is labeled comparison, just so I know what different determinations or runs I used in my comparisons. And then I have a column for X, so determining what the order of X is. I'm only going to get values for X for runs 4 through 6 because that's when the concentration of HCl changed, but ascorbic acid did not. And then the order of Y when the concentration of HCl, someone at my door. The concentration of HCl did not change, but ascorbic acid did. Okay, and then I do have a column for K. So we'll look at K and we'll fill some of these out when we look in number 4. All right, so how are you supposed to do this? So let's just start with let's start with the Y column actually, since we're starting with comparing ascorbic acid. Okay, so how do you actually do this? I'm going to click on the first cell. So basically what I've done is I've taken cell 3 and cell 1, and this is F. I've taken the K observed values and I've divided the K observed for, actually this is 1 and 3, excuse me. So I've taken the runs for K observed run 1 and run 3 and divided them by each other. And then I also did the runs 1 and 3 for ascorbic acid concentration, okay, and divided them by each other. So let me give you an example of why I did this. Why do I have log of F2 over F4 divided by log of E2 over E4? I'm going to scroll down and show you this. Oops. Let's just make that enter. Okay, so remember, when I'm comparing two different rates to each other, I usually have rate, and let's just say rate 3 in this instance, divided by rate 1. And that's going to be equal to whatever concentration does change. So in this case, it's going to be AA divided by AA for run 3. So we'll say this is, or for run 1. Let's say this first ascorbic acid concentration is for run 3, and the second ascorbic acid concentration is for run 1. And this will all be raised to the power of, in this case we call it Y, to the power of Y. So what are we trying to solve for when we're comparing? We're trying to solve for Y, right? We're trying to solve for what the order of ascorbic acid is. Okay, so how do I actually solve for Y using logarithms? How do I take that Y down and determine what the order of Y is? What I do is I apply the log base 10 to this side, and I apply the log base 10 to this side, and that actually brings my Y down to the very front. So it says Y times the log of ascorbic acid for run 3 over ascorbic acid for run 1 is equal to the log of rate 3 over rate 1. Okay, so then if I divide this entire expression over to the left-hand side, what I end up getting is Y is equal to the log of rate 3 over rate 1 divided by the log of ascorbic acid 3 over ascorbic acid 1. So it probably doesn't look super familiar to you because you haven't done this enough times, but that's where this formula, this calculation is coming from. It's from using logarithms to bring that exponent down so I can solve just for the order of ascorbic acid by itself. So moving back up, I'm going to highlight this for you again, this Y, so you can see what I've done. I'm going to click this. I have taken log of, okay, F2, which is run 1, divided by F4, which is run 3. And then I've divided that by the log of ascorbic acid for run 1 over ascorbic acid for run 3. that, evaluating that, putting that little equal sign, that gives me what the exponent is, which is y. So if you press enter, that gives you the exponent of 0.966, which tells you that the order of ascorbic acid is approximately a first order reactant. So I'm getting 3 values for these 3 different comparisons, and then after that you're going to get an average. So it's very close to an order of 1, a little low, a little bit lower than a perfect 1. But you're going to use that. You're going to do the same type of process to determine what X is. So for X, we're trying to find out what the order of HCl is. So we're going to compare runs 4 and 5, then runs 5 and 6, and then runs 4 and 6. This will probably take you the most time out of all of the other calculations that we're doing. So I would suggest to pause now and then take your time doing those calculations. I'll keep this highlighted for you so you can see what the formula is to solve for these exponents. And go ahead and pause the video and then come back when you're done. All right, so the last portion of the calculations, number 4, states that we need to use the determined values of X, Y, and the K observed values, and the concentrations for each run to solve for the true rate constant K using equation 3. Average the values determined for each run to give you your best estimate for K. So let's look at equation 3. Scroll, scroll, scroll. And then right here is 3. So it's actually really simple. Let me zoom in a little bit. So it's actually really simple. You're taking a K observed value, your K observed value that you have, and then you're setting it equal to K times the concentration of H to the X times the concentration of AA to the Y. All right, so we're basically going to divide the concentrations over here and then solve for K. So I have a column over here for K, and then I have 6 different values for the 6 runs, and then I have an overall average. Okay, so let's look at the first cell and see what I did. So for the first cell, to solve for K, and remember K is equal to K observed divided by the concentrations to their corresponding exponent. So what I did was I divided F2, let's see where F2 is, which is, let's click on this, right here. So it's K observed, that's this one value right here. And I divided into K observed my concentration of hydrogen H+, which was HCl, so that's B2, that's right here, to the exponent of H8. So what's H8? Let's look down right here, this is H8. This is the average for the X values that I solved. So remember in the previous step, you solve for 3 X values, comparing runs 4, 5, and 6 all together. So you should get an average for those 3. That's what's going to be the exponent right here, our H8. And that's multiplied by, so the denominator is multiplied by the concentration of AA, which is right here, to the exponent of I8. I8 is just the average Y value that you got. Okay, so if I was going to write that out just to make it more clear, I have it right here, right? My K observed is equal to K times H plus to the X times AA to the Y. So if I'm solving for K, that means K is equal to K observed divided by the concentration of H plus to the X times the concentration of AA to the Y. So that's essentially what I've put in to this cell right here to solve for this K value. Okay, the next one I did the same thing. So notice this is my second K value. But instead of taking F2, I took F3. So I took this F3 value, and then I divided it by the concentration of B3, which is the concentration of HCl in run 2, to the still H8. So I'm still doing it to the exponent of the average X value that I solved for. And then that's multiplied by E3, which is the concentration of AA, to the exponent of I8, which again is the average for your Y values. Okay, if you do that all the way down, you will get a value for K, and then I also solved for the average for my K right here. So this is my average K, average Y, and average X. So I'm going to highlight this. Go ahead and pause the video to make sure that you can get all of your averages and then calculate your K value. And then come back just to make sure that we have appropriately calculated everything. Okay, so now that you're back, let's zoom out of here and let's go back down to the calculation section to make sure that we did everything that we were required to do. So, calculations part 1, we calculated all of our A minus A infinity values, which is over here. You did it for each of your 6 runs. And then you plotted the natural log of methylene blue versus time. So, sorry, the natural log, in this case, of A minus A infinity, which is the same thing as plotting the natural log, excuse me, the natural log of methylene blue concentration versus time. So you did that 6 different times, and then remember your slope was your negative K observed value, which you took 6 of them and you put it right here in this column. Okay. Number 2, determine the concentrations of H plus and AA in each experiment. So that's what we did here, and that's what we did here. Next, in number 3, once the K observed values and concentrations have been determined for each run, use the method described in the theory section to determine the X and Y values. So we determined our X and Y values. That's what we did here and here. Let's see, you should be able to make 3 separate determinations for X. So that's 1, 2, 3. That's what we made. And then 3 separate determinations of Y. 1, 2, 3. Average the results for each variable and take the value to the 0.1 place as your best estimate. So essentially our best estimate then for the average of X would be 0.4, and the average for Y would be 1.0. So it looks like X, or the order of H plus, has a fraction of an effect. And then as our Y is basically a first order reactant. Okay, and then 4, use the determined values of X, Y, and K observed and the concentrations to solve for the true rate constant. Average the values determined for each to give your best estimate of K. And so this is my average for K. Now, you see other stuff over here. I was doing additional calculations to basically plot some other stuff and determine, like, use a graphical method to determine what the orders of each of my reactants were. You don't have to do that. You just have to do what's in the calculation section. So now you're officially done with the calculations. Go back to any part that was unclear. Let me know if you have questions. And this is what you're going to submit for your calculations for the Kinetics MB with AA experiment. You don't actually have to do anything by hand, just in the spreadsheet. All right, thanks.